Good morning. Can you all see the screen okay? Is the picture better today? Okay, much better. Okay. So you do see, I've changed some things. You can see the PowerPoint and the board, right? Can you see the PowerPoint and the board? Okay, cool. So I saw one question regarding the WebAssign. I know there's a couple of you who started the WebAssign with the old version. Just finish, if you can finish that WebAssign tonight, then do it. If you can and you need to go to the new version, just finish the problems. Those of you who started on the old one, just finish the problems, your assignment on the new one, and then I'll combine the scores at the end. Is that okay, Patrick? Okay. I'll deal with it. It probably won't show up correctly in the grade book, but I will adjust it later on. Okay, I will adjust the score just to make sure everything works out okay. All right. So yeah, the first homework is due tonight, so make sure you get done on it, get working on it. I probably will try to answer questions on the homework in the lab today, because we'll have some time in lab to discuss the homework. I was there to hand out lab kits yesterday, so I saw some of you folks pick up lab kits. So if you have not picked up a lab kit, there's today, but today is at NCC, and next Wednesday. You have to pick up your lab kit, because otherwise you can't do the labs. And if you can't do the labs, your score on the lab report will be 0. So make sure you pick up your labs. Okay, your lab kits. All right, again, today the lab kits are being handed out at NCC, and we will have one more day next week to pick up the lab kits. Okay. Make sure you read chapter 24 of the textbook on Gauss's law. It's going to be somewhat of an abstract chapter. We'll get through it. It's a little different. Okay. So just as a warning. And there's a worksheet associated with the material in chapter 24. It's called the Gauss's Law Worksheet. The worksheet is on Canvas. And what I would like for you to do is download the worksheet from Canvas and enter your solutions into the worksheet, and then upload it onto Canvas, where there's an assignment called Gauss's Law Worksheet. Okay, a question regarding this is regarding the 210R. Yeah, so the problem that you're doing, number 14 from chapter 23, yes, the 14th problem at the end of the chapter. Yeah, so if you have the textbook, or you can look at the ebook, you can just go to the end of chapter 23. The 14th problem is what you want to work on. Yeah, that's fine. That's okay. Anyway, just make sure you pick up your lab kits, and then Gauss's Law Worksheet is due on the 18th, Friday the 18th. Okay. And I'm going to expect that you will have a lot of questions on the Gauss's Law Worksheet, so please don't hesitate to ask questions. Gauss's Law is, at first, Gauss's Law is confusing, but once you get to understand it, it's not as bad. And, those of you who get it will say, "Oh, why didn't I understand that from the beginning?" At first, it's kind of a tough idea. Okay. Any questions or any other questions? Okay, so I made some changes to my display, so it does show up better when I make videos. Last night I created two videos I placed on YouTube. There are two more examples where I calculate the electric field due to a charge distribution, so you may want to take a look at them. If you have subscribed to the YouTube channel, once I upload something, you'll get an email saying that I uploaded a new file or a new video. Okay, so you might want to go check out the YouTube channel. I emailed you the name of the YouTube channel a couple of days ago. Okay, and if you don't remember it, I'll type it here. BC Physics, Rockland, California. That's the name of the YouTube channel. They're not high quality videos, but at least I'm hoping that the videos I place on there, at least the solved problems, will help you with the homework and help you to better understand the course material. And most likely I will do more videos at the beginning of the semester, mainly because this is a tough unit. As we progress through the semester, you will see me making as many videos on solved problems. Okay, so last time we talked about the electric field, and we also talked about the kinematics of the electric field. And so I want to say some more about electric fields, and I want to delve more deeply into the meaning and what we can do with this concept. So I wrote down on the board some things about the electric field. And if you remember, I had this this diagram in the PowerPoint, where I was able to determine the direction of the electric field due to a source. And we established that the electric field due to positive charges always points away from it, and the electric field with a negative charge always points towards a negative charge. And the bigger the charge, the bigger the field, because you know that the electric field for a point charge is kq/r squared. So we determined it by bringing a test charge in the vicinity of a field source and then investigating the force on the test charge. We took the force on the test charge and then divided by the value of the test charge, and that gives us the magnitude and direction of the electric field. And depending on where you are relative to the test charge, that allows you to assign a unique vector at all locations in space in which the field is defined. And this vector characterizes the space in the vicinity of the charge. So I can draw a picture illustrating that. If, let's say, I draw a positive test charge. I'll erase this. This is videotape, so you don't have to copy all this. By the way, as I'm going through a lecture today, please interrupt me if something sounds strange to you, doesn't make sense. So here's a positive test charge. I'm sorry, positive source. Let me use a darker marker. So this is a positive charge, and I can draw a vector, for example, that represents the electric field at this point in space. It will look like this. And then as I get further away, the direction of this vector stay the same as long as I'm going outward. The length gets smaller. And so what I'm doing is I'm assigning a unique value at all locations in space. These represent the field at these points, and the vectors are these fields. Okay? The direction of the arrow tells you the direction of the field, the length of the arrow tells you the size of the field. And I can map this out everywhere. So I can map these things out all over the board. I'm not going to do that because it's going to take too much time. But it'll allow me to draw something called an electric field line. If I take all these dots, right, and with the associated fields, and I draw lines that are tangent to these vectors, and I do this all the way around the charge, I get these lines that say something about the electric field. So basically, these red lines are connecting all these little vector fields. They're lines that are tangent to the vector fields. Okay. So these are called electric field lines. They're also called lines of force because if I put a positive test charge here, it'll tell me the direction of the force on that positive test charge. Michael Faraday came up with this idea because the idea of the electric field is very abstract to him, and he wanted a picture to give him some physical intuition of what the heck this means. And this worked for electric fields, magnetic fields, and gravitational fields. Faraday wasn't an expert at math. He was very intuitive in terms of understanding physics. And so he needed some way of understanding what a field is without really delving into the math. And so he came up with this idea. So what else do these field lines tell you? Let me play you a video.
By following the electric field vectors and connecting them with tangent lines, we can represent the electric field in a very powerful way. These electric field lines show the direction of the electric field at every point in space. The density of the field lines, that is, the number of lines that cross through a small surface area, represents the magnitude of the field there. The lines are more dense where the field is relatively strong, and less dense where it is weaker.
Okay, something happened with my video. I apologize. The video didn't play, just the sound played. Sorry about that.
By following the
So let me say something about the concept of the field line. One of the things you should notice is this. Suppose I'm going to draw a circle on the board, but in 3D this would be a sphere. Light-colored sphere. And in fact, let me draw two spheres. A big sphere and a small sphere. So their radii are different. They're imaginary spheres. What can you say about the number of lines that go through each sphere? They're the same. The number of arrows that you see going through each sphere is the same. Now, of course, these are representative field lines. I can't draw every single one, okay, because there'd be an infinite number of them. But based on what I've drawn, the number of lines going through each sphere is the same. However, on the largest sphere, the number of lines, the lines are spread out over a larger area. So the number of lines per unit area here is bigger than the number of lines per unit area here. Now, if you notice that if you're further away, since you have a point charge here, E is K Q over R squared. The further you are away, the smaller the field. And that corresponds to the fact that I have a smaller number of lines per unit area. So the further away I am from the charge, the smaller the field, but also the density of lines that's penetrating through this imaginary surface decreases. Right, the density of lines here penetrated this smaller surface is larger. That's because we're closer to the charge, the field has to be larger. And so Faraday suggests, okay, well, when we draw these lines, the number of lines per unit area passing perpendicularly through a surface is proportional to the magnitude of the electric field. The closely spaced field lines mean that you have a large electric field. We have a positive charge here. Notice that these red lines, they go from the positive charge all the way to infinity. They basically diverge from this charge all the way to infinity. Of course, for negative charges, these arrows will point to the opposite direction. They will point towards the charge. They come from infinity and go point towards the charge. As a result, if you have negative charge, the lines will point towards it. Positive charge, the electric field lines move away from it. When you draw field lines, they're either going to come or go to infinity or end up on a point charge. So, if we wanted to draw field lines that represents the field due to a charge or to a system of charges, these are the rules you have to obey to be able to draw them. Number one, the number of lines leaving the positive charge or entering the negative charge is proportional to the charge. So if I double this charge, I should have twice as many lines. Of course, that only works if I'm comparing, if I have two charges next to each other and I compare them. The number of lines I draw on one charge is arbitrary. But if I have a charge plus Q here and a charge plus 2Q here, the number of lines I draw here should be twice as many as here. When we draw the field lines, they have to be drawn symmetrically with respect to the charge. Okay, and it doesn't have to be a system of charges. It can be some kind of conductor, or it could be that's charged, or it could be some insulator that's charged. Now, field lines begin or end on charges, otherwise they go to infinity. And one of the important things is you can't have field lines that cross. Otherwise, that would mean that you have two values, two vectors that represent the electric field at the same location in space. And that makes no sense. You're assigning two different things at the same time to something. That makes no sense. Any questions on this?
So even like positive and positive field line across? Make like one big positive one?
Well, I cannot draw a field line here and then another field line like that, right? Because I know the field due to this charge at this location points away from the charge. Isn't that true? Okay, so I cannot say this can represent the field also, because I know there's a vector at this point that points away from that charge. It points downward. I cannot draw.
If you're dealing with two charges, would that still be true?
Yes.
Would you want to always combine their fields rather than drawing like field lines for each that conflict?
You draw the combination of the two.
Okay.
Right? You draw the two combined. Because if you draw two separate ones, that's going to be confusing. So when you draw the field to two or more charges, the field line that you draw is got to be due to the sum of all the charges that produce the field there. Does that make sense?
I think, yeah.
Because it's like saying you're driving, let's say you're driving, because if you assign two vectors at a location in space, I want to compare it to driving. Can you drive north and east at the same time? Don't say northeast because that's not the same thing. Right? If you're driving your car, can you drive north and east at the same time? No, you can't. Okay. Yeah, the video was confusing because the video wasn't playing. The video, only the sound played. Okay. I guess I don't have a fast enough computer. Here's an example of two field lines. So let me tell you what was done in this particular case. So you have a container full of oil. In fact, let me make the figure bigger. You have a container full of oil, and you have two conductors you place in the oil. Now, inside the oil, there's threads, and both.
The recording has stopped.
Uh-oh. 1 second.
This meeting is being recorded.
Okay. I'm having network problems. So you have oil, and inside the oil you have thread. The two dots that you see there are conductors. They both have the same charges on them. And notice how the thread sets up in the oil. In fact, look at right in between the two conductors. The field lines do this thing. It's almost like the field lines repel each other. You have two positive charges. And they're equal. So I have to draw the same number of lines leaving this guy as this guy. So the field lines, we'll do this. But then when you go in between, because they affect each other, the field lines will kind of do something strange like this. And this is what the thread's doing. If you look at the thread in the picture, in fact, right in the middle is an asymptote. Notice I've drawn so that to reflect the symmetry of the system. I have, since they have the same charge, I have the same number of lines here as I do here. Now, let me show you another figure. These are two oppositely charged conductors in the same material. And since field lines go from positive to negative, you'll see that in this Look at the string, look at how the thread forms lines in the oil. Yeah, you could say that they attract each other's field lines, right? Okay, except the ones to the left and to the right, they go off to infinity. The ones in between, they go from one to the other. And when you draw them, you just got to make sure they're equal charges, the same number of, so if the one on the left is negative and the one on the right is positive, if you draw 10 lines on the one on the left, you got to draw 10 lines on the one on the right, if they have the same charge. If one's double the other, then one's got to have twice as many field lines as the other. And this idea just gives you some intuition as to what the field line is, what it's doing. So let me, and I don't know if this video will play. I'm going to try it. We'll see if the video plays.
To the ground attachment of a Van de Graaff generator, we connect a large
Yeah, let me try one more thing.
To the ground attachment of a Van de Graaff generator, we connect a large conducting sphere. When we turn the generator on, the generator's sphere becomes strongly positive in charge, and the other becomes strongly negative. We sprinkle bits of fur into the air around the spheres. A very
I'm going to upload the videos on Canvas, and then you can look at them. I think I have too many things running on my computer, and it's causing me issues. Yeah, you're right. It's just that I have to go find the video. I don't want to spend the time right now doing that. Oh boy. Okay, here we go. Anyway, let me continue. Hopefully if I can restart that, I'll restart that. I guess I should restart it. Hold on a second. Just give me a minute. What's going on? So I want to consider some things regarding field lines. So let me erase the board here and let me say some things regarding the field line, just some math. By the way, the math can become very elaborate, and I'm going to try to stay away from that. So suppose I have, again, a positive charge, just to keep things simple. The same thing will work for a negative charge. And let me draw the field lines for the system. So let's see. And I'm just going to, again, draw two imaginary spheres. I'll draw a small one. I know they're circles, but in 3D, they're supposed to be spheres, okay? And I'll draw a big one. So this imaginary sphere is radius R2. This imaginary sphere is radius R1. And one of the things we said was that the electric field, the idea we're using is that the electric field depends on the number of lines per unit area penetrating perpendicularly through this sphere. So in other words, I'm saying that the electric field is proportional to n over a, where area a is the area of the sphere. And so what's nice about doing this particular example is that I know that all points on the sphere experience the same electric field due to this point charge, which are the same all the way around. I know that E1 is K Q over R1 squared. And I'm not writing this as a vector with a magnitude symbol on it because it's implied we're dealing with the magnitude of the vector. And I can do the same thing for E2. Okay. We said that E is proportional to the number of lines per unit area. So that means that E1 is proportional to the number of lines passing through this area divided by the surface area. Which means that this is going to be equal to the number of lines over the surface area of this little sphere. Let's go by that expression. And similarly, E2 is proportional to n over A2, and that's going to give us n over 4 pi R2 squared. So what if I take the ratio of E2 over E1? What do I get? Well, I get n over 4 pi R2 squared over n over 4 pi R1 squared.
What does n mean again?
N is the number of lines, it's an arbitrary, whatever the number is, the number of arrows that pass through this blue sphere. Does that make sense? So in this particular picture, there's 8 black arrows that pass through the blue sphere, correct? All right, 1, 2, 3, 4, 5, 6, 7, 8. There's 8 of them that pass through this blue sphere. And also 8 pass this blue sphere. I drew 8 arbitrarily. That's why I'm saying it's n. It could be any number. It's just a number. Okay? You know, n is going to depend on how you draw your picture. That's why I put a proportionality there. I didn't say equal sign. Okay, I didn't say equal. Because I'd have to know what the proportionality constant is. So when I do the math here, the n's cancel, the 4 pi's cancel, I'm going to get R1 squared over R2 squared. Remember what I said about the field lines. I said that the number of lines per unit area is proportional to the electric field. If that's the case, then E2 over E1 is R1 squared over R2 squared. So I better get the same relationship if I take the ratio of these two equations. And when you do the math there, these k's and q's cancel, and I'm going to get R1 squared over R2 squared. Which verifies the fact that the number of lines per unit area is representative of the electric field. That's all this exercise was about, to show mathematically that this is the case. Because I came up with it intuitively, I wanted to show this mathematically. Now, one can do this in general. I'm doing it for this simple example. Is that n given in problems? No. One question, is that n given in problems? No, it's an arbitrary number. This is one of the things that's going to drive students crazy. What's n? Okay, I drew it with 8. Maybe if you drew this picture, you would have had 16 on it. It's an arbitrary number. But I know the number is the same for this guy and this guy. Right, for the two spheres, n is the same. Okay? Stop me if you're getting confused. Well, it's a surface area, right? This is you got to think in 3D. These lines are penetrating the surface area of a sphere. And what's the surface area of a sphere? It's 4 pi r squared. So there's my 2 in the picture. And so this does agree to Coulomb's law.
Why don't we use what's called volume area? No, not area, but just volume in general instead of surface area.
Why did we use volume?
Yeah.
Well, because these lines are penetrating a surface, right?
Oh, like surface area of a sphere you're talking about. Okay.
Yeah.
Okay, gotcha.
Yeah, they're
Makes sense.
penetrating the surface.
All right.
Okay. Now, one more thing I want to say, and this is going to really be actually very important, and I'm not going to prove it in general. If I ever have time, I will, but I'm not going to prove it in general. This is going to be very important. So I want to look at if E is proportional to n over A, what's E times A? Well, E times A is going to be proportional to n. In other words, the number of lines that goes through any surface is going to be dependent on the product of E and A. So I want to look at this. What does that product depend on? And so basically all I'm doing is moving this A from here to here and saying the number of the total number of lines then that pass through a surface is just the electric field times A. Okay, I got to be careful though. Okay. Yeah, so whatever n is, you're right regarding the question. So the question is, so whatever n is, it will cancel out when we do E1 over E2, yes, because in this particular case, because the same lines go through each surface. Obviously, if I drew my surface here, that's not the case. So I'm saying that n is E times A, and I got to be careful. The number of lines that goes through the surface, and I'm running E times A. The reason why I can say that is because, one, the electric field has the same value all the way along the surface. Also, the electric field lines are always perpendicular to the surface of the sphere. Yes, you're right. I'm about to drop the flux idea on you guys. Sorry. Don't forget Cal 3.
It's a little goldfishy thingy between the equations instead of the equal sign. What does that mean again?
What's that? The fish symbol?
Yeah.
It means proportional to.
Okay, thank you.
So I want to look at the total number of field lines. And I should get the same answer whether I use this sphere or the big sphere. Is that true? Because there's 8 black arrows that pass through the blue sphere, and then there's 8 black arrows that pass through the big sphere. Well, let's look at E times A1, or E1 times A1. That's going to be K Q over R1 squared is 4 pi R1 squared. And then we're going to get K times Q is 4 pi. But K is 1 over 4 pi epsilon naught. Times Q times 4 pi. So the number of lines that penetrate this sphere depends on how much charge is inside the sphere. Okay? The number of lines that pass through this little sphere depends on how much charge is inside it and some constant epsilon naught. Now, I can do the same thing for E2, A2. And you'll see that you actually get the same answer. So the number of lines that penetrate either one of these depends on how much charge is in there. If there is no charge, then there aren't any lines going through here. Does that make sense? Isn't the number of lines a gimmick? Well, for electric fields it is, but if you're thinking of the flow of water in the pipe, yeah, you're right. It's a visualization aid, but it has a more physical meaning. For example, when you're using this idea to describe the amount of water flowing through a pipe. Well, we're not saying that it's equal to. We're just saying, in your case, in your question, Damien, we're not saying it's equal to, but we're saying it's proportional to. Okay. And yeah, that proportionality constant is going to be arbitrary because the value of n is arbitrary. But all we're saying is proportional to. And this is going to be an important term we're going to use in general. I'm not going to do this in general. In Calc 3, you'll actually probably see this done in general. It's a constant times that value. I'm sorry, what do you mean does it quantize it? Well, I guess since Q is quantized, you can say that, right? I mean, since Q is a quantized number, yeah, it does come in discrete value. That's a good point. I really never thought about that, but because this comes in multiples of 1.6 times 10 to the minus 19, then yeah, it is a quantized value. So is the number n, right? That should make sense. I mean, that's a really good observation. Yeah, I never thought about it that way, but since n is discrete, this has to be discrete. Okay. So the total number of field lines passing perpendicularly through an imaginary surface only depends on the amount of charge enclosed within the surface. If you have charge enclosed, we can call that as a source. There's some sort of source inside of here. Oh, by the way, this idea can also can be applied to the flow of heat in or out of the surface, or the flow of water in or out of the surface. So what I've done so far is a really simple case because the E has the same value all the way around the surface. But what if E varies over the surface? Or, in fact, let me do the following. What if I had something like this? Instead of using a sphere, I chose a cube. What if I chose a cube? I can if I want to. Of course, it's going to make life very miserable for me if I use a cube. And I'll show you why. Let me redraw this. I'm only going to draw one cube. I won't draw two cubes. Let me draw the field lines. So now I'm going to draw a cube around cube. Actually, I'll draw a box like this. It's probably better if I draw a box. But imagine it's 3D, it's a cube. And consider all these field lines. In fact, I should have drawn them in red. Okay, now what's happening here? First of all, the electric field is different all the way along that surface. Okay. It varies all the way along the surface. So I just can't say that the number of lines is E times A. I actually have to break the surface up into a bunch of teeny tiny pieces. Such that the field is constant over that piece. And then I got to add up all the contributions. Not only that, the electric field here is not perpendicular to the surface. So just think of this. Let me give you an example, an analogy. Suppose you have water flowing through a pipe. Okay, the water is going like this. The water's flowing this way. Okay. And let's consider a bunch of water that goes from here to here in a time delta t. How much water goes from here to here? Well, it's going to be the area, okay, times the velocity of the water, times the time interval. So area times time, which is your volume, and then a density, rho, will give you the amount of water. This is the amount of water, the amount per unit volume, the number of particles per unit volume, for example. Think about it that way. How many water molecules go through here? Now, once you get to this side, the velocity vector points this way, but the surface is like this. It's only the component of the velocity vector that is perpendicular to the surface that goes through the surface. Isn't that true? Only the component of v that's perpendicular to the surface goes through the surface. The same thing with the electric field. It's only the component of the electric field that's perpendicular to the surface. So basically, here's the normal to the surface. That's theta. This is E. So what goes through the surface is E dot N. So I have to figure out the component of the electric field that penetrates through the surface. Then I have to multiply by my little element of area. Then I have to add up all the components, all the little areas. And that'll give me the total flux through the surface. Now, if the field's uniform along this surface, that's a little bit easier. If I just have a uniform field here, that's easy to calculate. It's just going to be the electric field that passes perpendicularly through the surface times A. But then I got another term here, the component of electric field points upward times A. Plus the one that goes through here, goes here. There's 6 sides to the cube, so this will be a sum of six terms. So I have to break up my calculations so that E is constant over, actually not E, but E dot N is constant over the area. And if I have a system whose electric field varies continuously, the area that I'm talking about, the element of area, has to be infinitesimally small, which means I have an infinite sum of terms. That means I have to do an integral. So the number of lines passing through an area that is proportional to an integral called E dot N dA. Some people write just E dot dA and define n hat dA is called the area vector. Okay, you will see some folks, and that's fine. Some folks will say n is proportional to, actually let me write dn. dn is proportional to the electric field dotted with the normal to the surface and dA. And then they're going to define this as the area. We call it the area vector. We get right over that. And then we integrate this. And so the number of lines is proportional to this. But what did we say this was equal to? Okay, I didn't prove it in general, but I said that this is true. Okay, I made this statement with a real simple example. One can prove this, that is true in general. And this part here is called Gauss's law. This integral is called the electric flux. They Calc 3, you've heard the term flux before. Flux represents a flow inward or out of a surface. If the flux is outward, then we say it's the flux is positive. Okay. And so this integral, it doesn't have to be integral. You can write it. This is the field's constant. This is if the field varies in a discrete manner. And this is if the field varies continuously. It's called the electric flux. The electric flux and divergence are different. They're related to each other. And I'm trying not to say anything about the divergence.
The equation to the right, you said is continuous, and the other one to the left is not continuous?
In other words, if the electric field varies continuous over the surface, this one means the electric field varies discretely over the surface. And this one means that the electric field is constant over the surface. Right, this is general, right? This takes care of all three cases. Writing it this way, because if it's constant, I can hold E out. And if it varies discretely, this integral becomes a summation. Yeah, some of you folks are asking about the divergence. This integral is related to the integral of the divergence vector. It's the same thing. This integral, so that means that E dot n dA is the same thing as the divergence multiplied by an element of volume. So those are the Calc 3. Okay. Yeah, so if you integrate the divergence, that's the same as this. If you don't know what divergence is yet, don't worry about it. So I just remembered when I was a student and the instructor introduced this, then he said, okay, where did I lose you? I know this is weird stuff. Okay. So the net flux through a closed surface, it represents the number of lines leaving a surface minus the number of lines entering the surface. So if you do this integral over an entirely closed surface, okay, you see the integral symbol with the little circle on the integral symbol? That means you're integrating over the entire closed surface. If you do that, then your unit vector n hat is always directed away from the surface by definition. The two types of flux, the summation. You want me to go over these two? Okay, so this is, if the electric field is constant over the area, then you just take E times A. If the electric field is not constant over the area, then you got to break up your surface into pieces that are small enough such that the electric field is constant over that surface. You know, and maybe I should have given this example. Suppose I have an electric field that points like this. Actually, no, let me not do that. Suppose that electric field is like this. Okay? And let me draw a box. Like that. So the component, so if we look at this surface, okay, on this surface, it's only the horizontal component of the electric field that penetrates this one. Isn't that true? And here it's only the vertical component of E that passes through the surface. So I got to take the vertical component of E times A here, plus, I'm sorry, not the vertical, the horizontal component. The horizontal component of E times A here, plus the horizontal component of, the vertical component of E times A here, and I'm going to go all the way around. So I have 4 terms in my summation, one for each surface, and it's a different component, right, as you go along the surface. So I've broken it up into a sum of 4 terms. That's called the Greek letter phi. This is the Greek letter phi. It's capital. Actually, I should say phi. Okay. So this is phi. That's the representation for the flux. And the units is basically newtons per coulomb times meter squared. There's no fancy name. Let me go back one. And Newton meter squared per coulomb. If you do the integral over an entire closed surface, then you're going to get the sum entering and leaving. Okay. Now, let me look at this. Let's look at this square again. The normal to the surface always points outward. So in fact, this normal and this normal, in fact, all these normals point in different directions. This field, in fact, if you look at the y component, the x component of this field, it points horizontal. What can you say about the angle between these two? They're 180 degrees. So the dot product gives you a -1. Over here, the electric field, the x component electric field points this way. So E and hat point in the same direction. That dot product is going to be positive. Okay, and if the E sub x is the same here as here, then and the two areas are the same, they'll actually cancel each other out. Does that make sense? So that n hat's important. The direction of n hat with respect to E is important.
To clarify, that red box is a surface, right?
It's an imaginary surface that I drew.
Okay.
It's not real.
It's cutting through the field line, right?
Correct.
Okay.
Are we okay so far? I know it's getting weird. I'm going to skip
When
this
electric
video
field
because
when electric
it
field
won't play, so I'll let it go. So let me do an example. Let's say we have a point charge it's placed at the center of a ring, having a uniform charge density lambda. So the ring has a uniform charge density lambda. And I want to calculate the total electric flux through a sphere whose radius is smaller than that of the ring. So mechanically, what I would have to do is this. I'd say, okay, well, I want to find the flux through a surface that contains Q. Well, here's Q. Oops. Here's Q. Here's my surface. Okay, it's not concentric. Okay, now I have the ring around it. Let me ignore the ring for now. I want to calculate the flux through the surface. So I actually have to take the integral from E dot N dA. I already know the answer, but I'm just going to tell you what you have to do if you have to actually do this calculation. The electric field is radially outward. So E, I can write it this way. What can you say about the direction of the normal to the surface? Remember, the red thing is imaginary. How do we write the normal to the surface? Doesn't the normal to the surface of that sphere point radially outward all the way around the surface? And so I'm going to put that. And then my dA. Of course, my dA is just what? Well, this is the same all the way around, right? I mean, I can actually pull this out of the integral because the electric fields are going to be constant all the way around. R head is 1. And so I just got to integrate over the entire surface area. Well, this is the surface area of a sphere. I get 4 pi r squared. And I'm done. Okay, well, that's the same thing as doing this. Okay, that's what I was saying. This way is true in general. So really, I know the answer already. I know it's Q over epsilon naught. I don't have to really do all this work. Now, what if I make the sphere enclose the ring and the charge? In reality, if I had to grind through and do the calculation, it'd be horrendous because the electric field into the ring does not have nice behavior. This dot product would be nasty, and the integral would be nasty. However, I know that if I enclose both charges, then I don't have to do any work. Since I know Gauss's law, this is really Gauss's law, since I know it's true that the integral of E dot N dA over a closed surface is equal to Q enclosed over epsilon naught then I don't have to figure out what E is for the ring or the charge, and I don't have to take that dot product, and I don't have to do a horrendous integral. I just know that this is going to be Q of the point charge plus Q of the ring over epsilon naught. And then Q plus, since that ring is uniformly charged, then the total charge on the ring is going to be 2 pi times B, that's the length of the ring, right, the circumference, times lambda. That's my answer. I don't have to do an integral. Okay, so it's not as bad as it may seem. Here's another one that can look very intimidating. We want to consider a uniform field So let's say we have a field that points to the right. And I'm going to draw an imaginary sphere in this field. That's my imaginary sphere of radius r. I want to know how much, what is the flux going through the right-hand surface? And I say, whoa, how do we do that? You can actually, and I was doing this last night, you can actually set up the integral to do this. Okay? You can actually set up the integral to do this. And I thought it was supposed to be a bad integral, but it's not. You can actually set up the integral. You can actually set up the integral of E dot n half dA. So the electric field dot n is going to vary all along the surface because n half looks like this. This is the angle theta. This angle theta is going to change. So this is going to be the integral of E cosine of theta dA. E is a constant, but this is not constant. So I have to break this spherical shell into a bunch of rings and integrate over all the rings that make up this sphere to do this calculation. It's actually doable. It's not that hard. But notice something. How many lines enter on this side and how many lines exit on the other side? Are they the same?
Yeah.
Do the number of lines that enter this side, or is the number of lines that enter this side the same as the number of lines that pass through the center of the sphere? It's not? You sure about that? Okay. But it's the same thing. So all I got to do is consider the center of the sphere. And since E dot n is constant, because the center of the sphere is a plane that's vertical, E is perpendicular to the normal to the surface of this center. We call it a great circle. So basically, all I got to do is take the electric field times the area of this circle. And so phi sub E is just going to be the electric field times pi r squared. And by the way, the question is this positive or negative? Sorry about that, Damien. Sorry to the confusion. It's got to be negative, right? Because N points this way, the electric field points in that direction. So the field is going inward, right? The field is going inward on the left-hand side. So this has got to be negative. The field lines are outward on this side, and so the flux is positive. Well, because the normal to the surface is in the same direction as the electric field. All right, if you take the dot product, what theta is the angle between the electric field and the normal to the surface. So on this side, the angle is 0, but on this side, the angle is 180. On the left-hand side, then, you have cosine of 180, you get a minus sign. So I didn't have to do all the work. But just for fun, if you want to do this integral, you can set it up and do it, you'll get the same answer. Good practice. So, this is really Gauss's law. Right? This is Gauss's law. That the electric flux, which is the integral of E dot n dA, equals Q over epsilon naught, is Gauss's law. And it can be used, in the right cases, it can be used to determine an electric field due to a charge distribution. This is always valid. In fact, this is one of what are called Maxwell's equations. Maxwell was able to summarize all of this course in 5 equations. This is one of them. One can derive Coulomb's law from this equation. This is more general than Coulomb's law. And the reason why this expression works is because Coulomb's law depends on 1 over r squared. If Coulomb's law did not depend on 1 over r squared, we wouldn't have this law. So this exists because it's a consequence of the 1 over r squared nature of Coulomb's law. Remember, anytime we're integrating over a surface, the surface is just some imaginary sphere that we choose at our own convenience. So in this figure, I show you, in fact, let me blow this up real quick. In this figure, I have a charge Q, and I've drawn various surfaces around Q. No matter what shape the surface is, the flux through any one of those surfaces is Q over epsilon naught. Because if you look at the last 2 surfaces, if you actually had to grind out the integral, it would be kind of tough. It would be tough to do. But thank goodness for Gauss's law. It makes life a lot easier for us. Now, a lot of times when we work with Gauss's law, the Q net, the Q that's inside the surface, can be determined from some sort of charge distribution. You can have a distribution of charge that varies over a volume or over an area. So I've also written Q net as the integral of rho dV. Now, the dA is the area that's enclosing dV. Okay, the dA is the integral of the dA is the total area that's enclosing the volume. And you'll see more of these kind of things in Calc 3. So I have proved this Gauss's law kind of in a simple way, but there's a more general proof that you would either see in a more advanced physics book, like a junior level physics book, or you would see it in Calc 3, depending on the instructor. Like I said again before, Gauss's law is a consequence of the 1 over r squared dependence of Coulomb's law. And it really is Coulomb's law expressed in a different way. Okay, 1 second. Okay, so I'm going to stop here. I don't want to go through this example right now. So what I'll do on Monday is I will review this material, because I know it's not easy. I'll review some important points of this material, and then I want to do some examples. Okay, that's what I'll do on Monday. Do y'all have any questions? And I know this stuff is weird. It's the first time you see it, it's just bizarre, but it'll come to you. No questions?
Thank you for today's lecture.
Okay, so yeah, you're welcome. So we'll see you in the lab today, and possibly recitation. So let me end this meeting. So some of